Yes? Right shift. Josh, got it? Nice. Okay, shift up, shift down. Okay? So you can see that I'm okay, and then we have reflection in the x-axis. Okay. So again, remember, reflection in the x-axis is with the negative sign stuck in front of the function, right? G of x equals negative fx. That's reflecting in the x-axis. What's it reflecting in the y-axis? Does anybody remember? What's it reflecting in the y-axis? Sorry? Sorry? No, I mean generally speaking, what is reflecting in the y-axis? What about just the x? No, I'm not talking about exponent functions. I'm talking about, suppose you've got a function fx. You want to reflect it in the y-axis. To what? Okay. G of x equals f of negative x. Okay, the negative sign goes inside. Is everybody all right on this? Okay. Here it is, reflecting in the y-axis. Kylie, why is the mouth going? And then you're saying you're always kind of not finishing your notes. Now you just told me, wait. Got it? Emma? Yes? Scale? You do. You do. You don't get it? Get it, do it. What do you mean you don't get it? Scale, you do. Do it. Whatever number you like. How's that? How's freedom of choice for you? Oh, man, I'm very smart. Very smart. Cool. I like that. Okay, you guys going to scale this? Yeah, Thomas, what factor are you going to use for scaling? You're going to use 2 to the power of 2x. Whoa, man, that's pretty sexy stuff. I'll tell you why. No kidding, man. Oh, listen up. When I say sexy stuff, I mean mathematically sexy, okay? Get this straight. Get this straight, okay? God, you teenagers, man. Okay, so Thomas is saying he wants to take this. So let me write this as fx. He wants to write this as fx. And then he wants to do gx equals 2 times 2 to the x. 2 to the exponent. No. That's not what you scale by, dude. Scaling, remember? Oh, you've forgotten. Oh, my God. Then g of x is scaled by writing ax squared. You don't put ax in here and then scale it like that. Yeah, you don't do that. Okay, so here's a suggestion for you. Scale it the way I've shown you there. See what happens. So do the graph. Okay, do it. And let me stand up. Okay. Doesn't this become 2 to the x plus 1? Doesn't it? It shifts left. I mean, right there. What do you mean why? You can see it, right? G of x equals f of x plus 1. Isn't this a left shift? Hello, when you multiply, what do you do with the exponents? Oh my God. What do you do with the exponents when you multiply? What's x plus 1? Now this happens only because Thomas decided to make this a 2. Okay? Only because he decided to make this a 2. If Thomas had told me a 3, then there wouldn't be anything sexy about it. I'm telling you, you need to get that panda off your head, man. He's squeezing your brain so hard, man, you can't even think, dude.
No, it literally looks like a 2.5.
I tell you, all these smokers need to be shipped somewhere, right? They all need to be shipped somewhere. Okay. All right. Because they're not paying attention. Okay. If you guys copy the notes down, I can start explaining. And if you shut up, maybe something might sink in. But if you don't, then your brain gets confused. Okay, you guys got this down? So these two numbers here are pi and e. These are two really famous mathematical constants, okay? Famous mathematical constants. Well, that's why I wrote it big in red, man. What's your problem? Okay, so if you want to know what E is, you need to really pay attention, okay? E is nothing very strange, okay? It's a very specific number. E is actually a number that's like 2.718 da 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 da. It's just a number. Just as pi is equal to 3.141 whatever. Okay? It's just a number. So, if you have something like 10 to the 2, which equals 100, then e to the 2 is going to be some number. Okay? It's going to be some number. How do you get that number? Well, you go into your calculator. Okay? Turn it on first. Yeah, turn it on. And here's e. Okay? It's above the division sign. So, you can go second e to the 2. And that gives you a number. So there's nothing mystical about E. It's just some number. It's just some base. Okay? All right? And you guys know that back from Algebra 0, you know that's an analog of this called an ln function, the natural log function. And then there was the common log function. Okay? And we're going to get to that next week, on Wednesday, probably. On Wednesday. Should have really learned in Algebra 1, too. Should have been part of Algebra 1. Okay, now you okay with E? Is there anything scary about it? Nothing at all. Oh. Okay, how about graphing this function? Just use your n box. You guys know how to graph this using your n box. Yeah. Okay, so if you graph this correctly, you should get something that looks like that. Okay. Okay, is everybody all right on graphing this using an n box? Okay, Sona. Sophia, got it? Sophia, Priscilla. My bad, I don't know. Priscilla. There's a Sophia that sits exactly where Subir is sitting. Yeah, Liao, right? Liou. Okay, does everybody know how to graph this stuff on their graphing calculator? Okay. Next one. This one will get your attention because you see money. See money. Okay, so you will get this down so I can start explaining this to you. All right, so for n compoundings per year, okay, so this is what we mean. This guy is called a principal, meaning the initial amount of money you put away in the bank. Okay? R is for rate, the percentage rate that you get. Okay? N is the number of compoundings. So if you are compounding annually, N equals 1. Semi-annually, N equals 2. Okay? Quarterly, daily, and assuming it's not a leap year, 365. Okay? Alright, you guys with me on that? Okay, see how I'm just addressing you? That's trash on that side of the room. Okay? Alright, you guys with me on that? And T will be the duration that you're going to keep the money away in a bank. Okay? Could be a year, could be 5 years. In your case, hopefully you're putting money away for 20 years. No, when you go to college, 3 years? Oh my God, you guys are going to be spending money here pretty soon. Okay? And then this is if you are compounding continuously, meaning every nanosecond of the day, your money is earning some interest. So what really happens is that in calculus, you learn a trick where this guy becomes that. So this formula becomes this formula if you're compounding continuously. Okay? So when you go put money in a bank, you go to ask, don't just ask them what's the rate. You go to ask them, what is the compounding method you're using? Are you doing it quarterly? Are you doing it annually? Or are you doing it continuously? Okay? Well, here's a really nice example for you to work on, okay? Yeah. Now, this is a true story, okay? I had a student here back in 2005 who was interested in buying an SUV. Back at that time, she was a junior, and she wanted to spend $40,000. And I tried to convince her that I don't think it's a good idea because you can make more money if you put it away in a bank and wait till you graduate from college, and then you can really go spend that money. So this example will illustrate that to you. So get this down and then crunch away, and this is what I want you to do. Elaine, can you stop riff-raffing there with the riff-raff? Okay? So make a table like that, fill it in, and appreciate the difference that continuous compounding can do for you. Okay? And I'll stop here.